Let me just go ahead and introduce our first keynote speaker. So Professor Nika Haghtalab is an assistant professor in the Department of Electrical Engineering and Computer Science at UC Berkeley. She works broadly in theoretical aspects of machine learning and algorithmic economics. And Professor Haghtalab's work builds theoretical foundations for ensuring the presence of everyday economic forces of learning algorithms for the integrity of social and economic forces that are born out of the use of machine learning systems. So she received her PhD in computer science at the Carnegie Mellon University, where her thesis won the CMU School of Computer Science Dissertation Award. And she is a co-founder of Learning Theory Alliance. Among her honors are Alfred P. Sloan Fellowship, NSF Career Award, Schmidt Science Fellowship, Google Research Scholars Award, NeurIPS and ICAPS Best Paper Awards, and EC Exemplary AI Track Award. So several industrial awards and fellowships on top of that. So with that, Nika, welcome, and we can't wait to hear your talk. Thanks.
Thank you so much for the introduction. I'm really excited to talk to you guys about foundations of multi-objective learning. From science fiction to industry to academia, the holy grail of machine learning and artificial intelligence has been, for a while, about learning general purpose models that excel at many tasks and many domains and many applications. And we're beginning to, especially with recent advances in AI and ML, we're beginning to see some success in this way. And this has started to encourage us to really think and move beyond specialized models, specially trained for specific tasks, and think more broadly about what it looks like to have models, perhaps a single complex model, that can achieve many different, can succeed in many different application domains and downstream tasks. So with that in mind, what is really happening is that we are finally able to both embrace and operationalize on the fact that a powerful model needs to go beyond a single objective. Typically, we think about an objective as like an average accuracy. It needs to really go beyond that and actually capture many different objectives in many different dimensions. So even if you're in your mind, if you think about wanting to have, for example, a risk predictor for diabetes that looks at a person and says, what are the chances that person is going to develop diabetes in the next 5 years? You want to move beyond accuracy, especially average accuracy. You want your predictor to be accurate no matter what the age of the person is, no matter what their gender is, what their race is. You want to have low type 1, type 2 errors. You want your risk predictor perhaps to be very well calibrated so it means what it means. You also want to think about if you were to use these risk predictors and then provide certain treatment options and propose treatments automatically, what those treatments have to satisfy. They have to align with human values. They shouldn't propose things that are unsafe for the person, and so on and so forth. So when you think about this, even in a very simple setting, we have to think about a single loss function, single objective as what we are striving for, and think about models that can actually satisfy many different objectives. So what I will argue is that multiple objectives and this multi-objective learning, these general purpose models, this is more about not just capabilities, but it's also about reliability. In the sense that on the capability front, yes, we want models that can satisfy many downstream applications, but also on the reliability front, we want good performance no matter what subpopulation, especially recognizable subpopulation, we want these models to perform well on. And the fact that they should perform well on no matter sort of what unpredictable environment they're placed in, and no matter what kind of adversarial or perhaps even malicious behavior they start to experience once they're deployed. So this is both about capabilities and reliability. And I'd argue that while we have started to see some performance improvement on the capability front, we're definitely seeing more capable models. There's no argument there. I don't think we've actually found a right way to actually think about multiple objective learning and provide multi-objective learning guarantees. And this is evidenced by the fact that reliability and fairness continue to be big issues for our models. Reliability in the sense that even when we try to have safety trained models, these methodological approaches to jailbreaks systematically continue to persist for these models. Also, in the fairness front, we continue to see unequal performance across race and gender for many of our models that are currently deployed in real life. So in a sense, we are lacking. Our current approach to how we are getting our general purpose models is lacking two things. One is that it's lacking a mathematical and provable guarantees, and those are really important, much more important perhaps on the reliability and fairness front than others. And also, it's somewhat lacking an algorithmic and conceptual framework to think about how do we fundamentally train a model, create data sets, and go about building something from ground up that comes with multiple objective learning guarantees. That's what this talk is going to be about. Designing multi-objective systems from ground up and sort of approaching this from a very fundamental foundational perspective. Some of the questions we try to address in this very short talk are about what does a mathematical framework for capturing multi-objective guarantees look like? What are the design principles when we think about having machine learning algorithms that satisfies multiple objective guarantees? And how do we go about designing algorithms, designing a toolkit, optimization toolkit, and even a data curation toolkit for this setting? So for this talk that is going to be about foundations of multi-objective learning, I will start with one sort of an umbrella, a unifying framework for capturing multi-objective learning. And then I'll talk about the toolkit of designing algorithms with these guarantees, talk about some technical insights, and I'll end by thinking about, beyond today's talk, what are some really important aspects of multi-objective learning that needs to be addressed, and hopefully you guys will also think about them in your research. So to start, to think about a framework for capturing multi-objective learning, I want to go back to the example of the risk predictor for diabetes in the next 5 years, to think about where is the data coming from, what are those domains, and who are the stakeholders in these decisions. So in a sense, we might be thinking about, we want to have risk predictors that no matter what hospital or medical center this risk predictor is deployed on, it actually does provide reasonable guarantees for the population represented by those hospitals. So you might think about a hospital that's a children's hospital, so it has a very different type of patient population than a hospital that is serving patients who are already suffering from some renal failure. Or a women's health center versus a center in a rural America. So these definitely represent different types of populations of people. And no matter sort of where this risk predictor is going to be deployed on, we want to make sure that it's going to have good guarantees for the populations represented. So here, there are stakeholders at the level of hospitals. Those might be actually the centers that can give us the data. We cannot maybe arbitrarily go and look for data, but we can go to these centers and hope that they will participate in our learning algorithm and provide some of their data, do some testing on our behalf. There are also actual individuals who are represented in these hospitals. And there is the learning algorithm and the model provider and deployer. So in essence, what's happening is that we have many different agents with their own individualized needs and limitations and hopes. And I would argue that multi-objective learning is really about enabling these learning processes to satisfy multiple objectives for many different stakeholders from collectively fewer resources that they would have needed to go about solving this problem by themselves individually. So with that in mind, one proposal for a mathematical framework that we will be using in this talk today is the following. Let's go back to the hospitals that we were thinking and the patient populations represented by these hospitals. We can think about them as being k different distributions. These are distributions over xy's, the feature vectors and labels. And we can actively go and take some more samples from these distributions by asking the hospital to provide some of their data to us. We might also have many different loss functions or objective values. So a typical way to think about the loss function is maybe we have a classification task and we have a binary classification, so a binary loss. But beyond that, you can think about maybe perhaps you want, your false positives or false negatives to be small. So you can design a loss function specially designed for reducing those. So with that in mind, the multi-objective framework that we will be working on today says that I want to learn a single function f that is simultaneously good no matter which of these distributions is evaluated on, no matter what loss function is being evaluated on. So, so what this means is that in a classical sense of machine learning theory, you have one distribution and one loss function, and you want to minimize that and provide guarantees that that's not going to be more than epsilon. In this case, what we are saying is that you want that guarantee to hold, even for the worst case distribution, even for the worst case loss function. And whenever that's actually possible, is what we call uncovering a universally good model. And you can, for the most part, just think about that this is truly the setting we are in. But I do want to acknowledge that sometimes this is just impossible based on the representation of your model. If your model is not expressive enough, you might find that that's not possible to do. You cannot find a universally low loss model, in which case you try to do as best as possible by competing with the loss of the best model when evaluated on worst case distributions and worst case loss functions. I do want to acknowledge that this is only one perspective, but I find this perspective to be really fundamental in the sense that usually when I give this talk, it starts to get people thinking about what would I have done to design a multi-objective system. And some of the other examples that one might come up with is thinking about, well, perhaps I can personalize the functions. I don't need to learn a single function. Let me personalize the function. Or to think about, I actually want to make sure that on any distribution evaluated is as best as possible. So this is called sort of minimizing per distribution benchmarks or competing with per distribution benchmarks. While these look at face value different from the model I'm proposing, actually really embracing that perspective in the orange box enables you to provide guarantees for many of these other formulations that come to mind. So with that in mind, let's stick to that orange box formulation for today's talk, as we know that it does actually generalize beyond what we are talking today. And for concreteness, since this is also a short talk, I'm going to really focus the rest of the talk by saying that I will have many different distributions, but let's just take a single loss function. Everything I say generalizes to having multiple loss functions, which is also important for many applications. Okay. So what's nice about this framework? I like this framework for many reasons, but two that I want to highlight is about how it provides a unifying perspective on a number of considerations that have been coming up in recent years, especially as it relates to reliability, fairness, robustness, and collaboration in machine learning. So when I first started thinking about what multi-objective learning guarantees look like, I was really inspired by thinking about collaboration needs, like in a sense of a federation of systems actually learning together and sharing their data to some extent. In that language of collaborative learning, the distribution DIs essentially represent different agent distributions, and these agents are willing to collaborate. But it doesn't have to be about collaboration. In fact, for recent years, this is also a setting that people think about some notion of fairness, where the DIs are representing different types of populations, usually socioeconomic factors come in. For robustness, the model that is specifically called group distributional robustness is an example of our multi-objective learning, where the distributions, again, represent some possible distribution shifts that you might encounter in the wild, and you want to be robust to those. And a number of other works have also, for fairness and calibration perspectives, have come up that fall under the umbrella I gave you. Honestly, I am here limited by how much I can put on a slide and how much time I want to spend on this slide, because I don't know how many I gave, maybe 7 or 8 examples here. I can continue putting examples up online. And the main point I want you to take away from this is that this is a fundamental problem. So rather than like thinking about special instantiations of it, let's actually embrace that fundamental problem and think about how you would go about designing systems that would meet the fundamental objectives you want. The second thing I like about this model is that I think about it as a very simple generalization of classic models of learning. For decades, we have thought about learning in a single distributional setting where we have one distribution and we want to perform well on it. And as a result, we have a very well-developed theory and actual practice of learning. And that, from the theoretical side, actually looks like something called statistical machine learning that says that I have sample access to a distribution. How much samples do I need to learn about that distribution? It's a very well-studied problem since the 80s and 90s. And we are really saying that, OK, it's a very natural generalization of this problem we have to be thinking about from a fundamental perspective. I have multiple distributions. How much does it take to learn about these distributions? And it helps to have a very rich foundation here, because both for comparison and to import insights, we have to do more than what's done for a single distribution setting. So we need to understand and sort of use those tools to start with. To ground some of the results I will show you in this talk, it's helpful to know what it is that we know in the statistical learning framework. And there are two insights that come up there that I think are worth highlighting for this talk. One is that if you have a distribution, essentially the best thing you could do is to try to minimize the empirical risk. That empirical risk minimization is to take a data set and just do gradient descent or whatever you can do to achieve best performance as possible on your sample set. That's the algorithmic paradigm there. There is a sample complexity paradigm that says that something like BC dimension, but if you don't like BC dimension, think about a proxy for the number of parameters of your model over epsilon squared is enough to provide epsilon error guarantees for what you're shooting for. So what you're asking in the sense of multi-objective learning is, what is the algorithmic paradigm? Is it still empirical risk minimization, or is it something else? And what is the sample complexity paradigm? Is it still something about the proxy of the number of parameters over epsilon squared, or something else? And we need to answer both of these questions fundamentally. OK, so this was kind of the setting I wanted us to think about for the rest of this talk. And what I'm going to do next is to give you some insights about the big questions of how would you approach algorithm design, how would you approach sample complexity questions in this setting. So with that in mind, let's just try a few very simple things that one might try at first. Remember that multi-objective learning is you want to do as best as possible on any loss on any distribution. And one turns out ineffective approach, but one that typically as machine learning researchers and also practitioners we try first is to just throw more data at the problem. So throwing more data at this problem turns out to be very ineffective and not the right way to go, but I still want you to see it. So what does this look like? Take a very simple data set. This is a version of MNIST data set, in fact, and think about capturing performance on specific subpopulations of this data set. What this graph is showing to you is the accuracy of the model you're learning. And each of these curves is one of the tasks that you're learning. So what happens here is that, to think about, ERM is typically for average accuracy, for a single loss function, single distribution. And the average accuracy actually gets minimized much faster than the worst case accuracy. What this really means is that if you were to throw more data at the problem and run your optimization algorithm on larger sample sets and for more iterations, what happens is that the average loss is not a good proxy for the maximum loss or the worst case loss, which means that even if there was no label noise, everything looked very consistent, you still have to run your algorithm on much large data sets to actually try to localize on the hardest subpopulation and hardest data set. Even with no noise, some distributions are just harder than others, and average loss is not the right indicator of that. With noise, things are so much worse because they can actually, like some distributions can cause other distributions more problem. And also the ease and difficulty of a distribution is not something that's decided in isolation. It's very much decided with respect to its performance compared to other distributions. So the takeaway here should be that while throwing data at the problem, in many cases does solve our problem, for multi-objective learning, it's not a particularly effective way of going about getting those guarantees. So you need to think about more than just how to scale your data sets. So we can actually formalize this. This wasn't just one experiment. Even in a mathematical conceptual way, you can show that there is this kind of an impossibility and gap. In the sense that what's wrong with the previous slide, or throwing more data at the problem, is that in a way, in fact, any approach that would have wanted to take an a priori fixed sample size from all the distributions has this pitfall that is ignoring the varying degrees of difficulties of different distributions and different tasks. And if that's the paradigm you're thinking about, which is collect some fixed amount of data and then do optimization, you actually fall in this trap that says that the number of samples or the size of the data set that you would have needed is in fact k times the size of data set you would have needed to address any one of those individual tasks. Let's take a second to understand what this is saying. What this is saying is that without some kind of an adaptive protocol to collect and curate your data set, so if all you're doing is to scale your data size, then multi-objective, multi-distribution learning doesn't save data, in fact, or save any resources compared to having learned a single, specialized model for each of those tasks independently. So this is really unfortunate. It's particularly unfortunate for if you want multi-objective guarantees for reliability and for multi-agent collaboration, because essentially it says there's no reason to collaborate, and reliability can only happen if you take, if you imagine every possible way that things can go wrong and take a lot of samples from those worlds. So this is a very unfortunate result, but only if you continue to think about the algorithmic paradigm of scaling your data and doing nothing else. So to go around this problem, what we have to do is not to take fixed data set sizes from distributions that are a priori fixed, but to actually think about how to on-demand sample based on what our needs are. So essentially what you're saying is that to effectively learn with multi-objective guarantees, the learner absolutely has to actively curate and shape the data set that it's working with, not just scale that data set. I call this on-demand sampling, and at a high level what that means is that you generate training data from wherever it's needed, whenever it's needed, not something a priori decided. So what does on-demand sampling look like? In fact, if you think about sort of some of the big parts of modern ML that we're thinking about these days, on-demand sampling and the need for it provides some insights and implications. So let's start with self-generation of data sets. This is something that's getting a lot of traction because we're thinking about self-generation of sample and hints as a way of even reasoning better, as a way of providing more accurate data sets. What this means is that the only reason self-generation, or the only way self-generation can help, is if you actually have either an algorithmic or a manually sort of designed filter there that looks at what self-generation does and filters out some good data from bad data before feeding it back to the model. So that's one implication for self-generation. It doesn't come for free. Another implication is for federated learning. Federated learning is one area where you actually actively can curate your data sets by deciding where to take these data from. So when you have many different sources, you can decide actually which of these sources to query and when to provide these guarantees. And lastly, on the importance and necessity of fine-tuning, in the sense that the need to go back and take some more samples from some task is something that at least fine-tuning addresses at a very, very sort of a one-shot way, where it first trains something and then once more it revisits the data set for a task that's needed. So what the implication of the previous result is that even if your task was represented at a pre-training time, for some of those tasks, you need to go back and fine-tune by adding more data from that task. Otherwise, you needed your pre-training data set to be k times larger. Okay? So these are some implications for modern considerations in machine learning that a simple gap in what is needed in terms of multi-objective sample complexity provides. Now, how do we actually go over and try to improve this unfortunate guarantees, an unfortunate gap, and provide a guarantee that doesn't increase linearly in K? So with on-demand sampling, and in particular what I mean as an example of an on-demand approach is to collect your sample sets adaptively. And what that could look like is that you take some samples perhaps from some distributions, and then you look at the intermediate performance of your models on the current samples, and then decide that you need more to collect more samples from some of the distributions again. If you do this, what you can show is that there is an algorithm that provides multi-objective guarantees with a blow-up that's only logarithmic in the number of data sets that you want to, or downstream tasks that you want to have a good performance on. So this is great because logarithmic things, we almost sometimes think about them as being constants 5 to 10, whereas linear things are definitely really, really large. In fact, let me, for those of you who like to see a little bit more fine-grained mathematical guarantees, to give you the real mathematical guarantee here, which essentially says that this is even better than logarithmic in the sense that you essentially are doing a single task in terms of complexity of your model, and then additively you have to pay a little bit of a cost. And that captures nothing about the difficulty of how large was your neural network you were training. It's just about your tasks. Whereas if you're non-adaptive, these things compose multiplicatively. So the complexity of your, the number of parameters of your neural network has to multiply by the number of world in which you want to think about having downstream guarantees. So the lower one is even nicer than the log K that I provided. It's an actually additive bound. OK, so I gave you some insights as to the gap between if you were to not actually algorithmically on-demand sample what happens versus if you actually go and on-demand sample. What I'm going to do next is to give you a little bit of insights and examples of what algorithms actually look like. I told you it's about on-demand sampling, but I'm still quite vague as to what that means. So I'm going to remedy that in the next few slides by giving you a framework of thinking about on-demand sampling. And I want you to remember that in the statistical learning sense, that single distribution, we said that the algorithmic paradigm was empirical risk minimization, right? Get your data set, just do as well as you can for that loss. So we are going to see the counterpart to empirical risk minimization and what that has to be for multi-objective learning. What I like to think about the counterpart to empirical risk minimization is just some minimization over some value, is actually imagining this as a zero-sum game. So what is a zero-sum game? A zero-sum game, this is the objective we want to provide. A zero-sum game has two agents in it. These agents are hypothetical agents for us, and a loss function. Here, the loss function is that L of D H star. So one of these agents is trying to minimize this loss over its action sets. The actions could be the set of functions that it has access to. The other is trying to maximize this loss. The actions are the distributions it can be selecting from. The nice thing about writing in this sense is that, in some sense, what we are really looking for is to provide this approximate min-max equilibria guarantee, which is that we are trying to find a solution that is optimal in a min-max sense. That's all that it means. So whereas empirical risk minimization was just to minimize something, we are trying to minimize the max of something now. Okay? So why is it nice to think about it this way? Because just as for decades we have understood empirical risk minimization, there is also a very rich history, particularly coming from game theory, about understanding how you can compute min-max equilibria and min-max solutions. And there, one very natural dynamics that you could do is to think about these two hypothetical agents, each playing a learning algorithm, in fact. What learning algorithm? Well, one of them is being a no-regret learning algorithm, making decisions online as it goes, hoping not to regret the past decisions. And the other one could be a no-regret, or in fact, what's called the best responding algorithm. Best responding algorithm is essentially an empirical risk minimization. So what we are saying is that, in fact, it's sufficient to have one player being no regret, while the other being the empirical risk minimizer. But game theory alone is not enough to actually tell us how to do this. And one reason in particular is that in a game, the loss function is usually a matrix given to you. You know if you play each action, who is going to get what loss and what value. But here, that loss function is the thing I don't know. I don't know the quality of a hypothesis, of a function on a distribution a priori. I actually have to sample that. I have to get some information about that. And this is where we differ. So what we have to do, which is where sample complexity comes in this algorithmic approach, is to think about the number of samples that you need to think about the quality of estimators you're providing about the game, as well as how long those dynamics get to solve the game you're looking for. So if you're applying a no regrets sort of guarantee, how long do you actually have to run your algorithm to converge to something? And both of these impact the sample complexity. I want to, without providing mathematical guarantees, we won't have time to actually prove this, but I still want to give you an example of an algorithm in this case. So the example of this algorithm is when I think about the two hypothetical agents, one playing a no-regret algorithm and the other being a best response algorithm. We'll start with the best response algorithm. That's the minimization. So remember that this is the player who is hoping to minimize the loss as evaluated on a mixture of distributions. And in fact, all it's doing is that it's picking one function. Okay? This is empirical risk minimization, with the caveat that rather than that being measured on a specific predefined distribution, that empirical risk minimization is actually happening on some distribution PT that is decided by our maximizing agent. What does the maximizing agent do? Maximizing agent is actually deciding that PT in a way that it would be no regret. What that means at a high level, I'm sure many of you are familiar with no regret learning, but for those of you who are maybe not as professional or you want to remember what that means, a no regret guarantee here, it means that the agent is maintaining some weights over all possible distributions. These are alphas, and they can change over time. And these weights are some proxy of the difficulty of the distribution that it has to learn. And what it's doing is essentially, by being no regret, it's making sure that the average loss in hindsight for the worst case distribution is not that much harder or easier than the losses of the distribution it's constructing over time on average. Okay, so algorithmically, in terms of pseudocode, what could this look like? You are taking samples. You have to take samples. And both of these hypothetical agents actually take samples. The first hypothetical agent, the ERM, has to take samples to perform ERM, and is taking samples from those PTs. The second agent, the no-regret agent, also has to take samples, because what it has to do is to actually construct these proxies for how difficult the distribution is, how poorly it's been treated by what has been learned by the other agents so far. So it has to take some samples to estimate that. They both interact with each other, and this is on-demand sampling because the samples that one agent is taking is defined by the actions of the other. In particular, the empirical risk minimization on-demand samples from PT. That kind of means that it's like sampling in proportion to alpha ITs, okay? To where these distributions, the difficult distributions are. So this is why it's on demand, because it keeps changing. Today, maybe I take samples from D1 to DK somewhat uniformly at random. Tomorrow, I'm going to focus more on D2 and D3 because they were the hard ones. And the day after, I realized it was actually D1 that was the difficult thing. That's why it's called on demand. I will not go into how you would prove that such an algorithm has guarantees. But for those of you who are interested, I recommend that you take a look at some of our papers. This is what I think is very interesting here, is that both game theory and machine learning actually have to come together to provide these types of guarantees. And this line of work has enriched both of these areas of research. I do want to also say that beyond providing provable guarantees, one nice thing about this line of work is that also empirically, it does do much better than previous algorithms. Now, let's say that I did focus and emphasize that it's important to collect your data adaptively. But even if your data sets existed and you couldn't adaptively collect them, they just were given to you, this actually does have superior performance compared to other works. And it does provide a very natural insight. And the insight it provides is that the state of the art of methods for this type of optimization prior to what I presented to you used to be that even if you have a sample set, you reweight your sample as you go, and you do optimization based on that. The insight that comes from our work is that the reweighting is not enough. Reweight and resample. In a way, subsample. This is like self-generation again. You're self-generating, but instead of just self-generating by changing the weights, actually introduce additional randomness. And when you do that, you see that the blue are our method's guarantees. Across the board, it's doing much better than if you were not resampling and you were just reweighting. And of course, it's doing so much better than if you were just throwing additional data with ERM. So this is, again, one nice example of where theory and practice came together. And in both, we are getting provable guarantees, and we are actually getting improved performance guarantees, even on existing data sets. OK, so this is all I really wanted to talk about. But I do want to end with some pointers to important considerations that this talk didn't discuss. But I'm super excited about thinking about them in my own research, and I think you should as well. So first, let's say that those of you who want to see the technical details, there are two papers especially I recommend to you to take a look at. And they have been also showing that not only we have good multi-objective guarantees, but for specific needs like reliability and fairness, we're doing much better than the state of the art from before these results. But in terms of what remains that I think is really important, the first one is I think we really need to think more about what it means to have agency and actually stakeholders' incentives in mind. Let me give you just an example of what this might look like. That beyond accuracy levels, like especially if you were thinking about the hospital setting, they have their own data sets. So they have to want to provide the data sets to us. We need to move beyond accuracy and think about the cost that a hospital might incur to give us their data set. And it might be a privacy cost, or it might be many other costs, like if any physical testing was needed to actually figure out if someone has specific genes. That's a lot of the cost that's borne sometimes by different stakeholders in this setting. So we need to make sure that beyond accuracy, people actually are willing to give that cost in return for the benefit they get from the learning system. And let me tell you why this is such a pressing issue. Because currently, this is not at all what you're doing. And in fact, the current algorithms are very much not beneficial for a large set of population. At least they appear to be that way. So again, for simple data sets, what you could measure is that the state of the art of algorithms that bring data sets together, these are federated algorithms, have this property that most of the agents think that they're not getting a good bang for their buck. In the sense that most of the agents think that they should have given 5% of their data set, not the entire data set, and they would have received essentially the same accuracy guarantees. This is a problem. Even if 10% of the agents actually don't give their required sort of samples and data sets, the entire system collapses and nobody gets a good outcome. So we really do need to think about these incentives. I think these are really pressing issues. And we should really think about how do we design platforms that actually provide multiple objective guarantees for multiple agents, thinking about their incentives. Those of you who are interested, this is something that I've been thinking about more and more these days. So we did highlight these issues in an ICML21 paper, but we also have a very new result that says the importance of role of platforms about bringing people together and kind of mathematically how should those platforms be designed. So again, if you're interested, I recommend that you take a look at this literature. So this was about agency and incentives. The second thing that I think is really important is to think about where those loss functions came from. For today's talk, we just assumed that somebody gave it to us that said that, okay, there are many losses, but these are the losses you should be really thinking about. But I think for many of these applications, when we think about losses not just as calibration losses, accuracy losses, but as ways that humans might tell us about their value system for what they want to see in a system, it's not reasonable to assume that you have a loss. So just as we know that learning from human preferences for alignment and other issues is really important, multi-objective guarantees should also come with the ability to learn from human preferences and human values. So that's, I think, a direction that's really important to think about. How would you go about actually not just learning from human values, but aggregating and learning them in a way that's appropriate for multi-objective guarantees. And the last thing I want to highlight is that we did talk a little bit about what it means to self-generate data sets, and especially because that's a really timely, I think, perspective. It's important to understand what does multi-objective learning says about the right ways, responsible ways, and sound ways of generating data sets in a way that actually do augment, the augmentation of your data sets actually means something provably for the performance that you're observing. I think this is also a very important area of research that I encourage you to think about. But that really what I'm asking for is for you to join this kind of addressing the need for mathematical foundation for multi-agent, multi-objective collaborative learning. And I want to say that many people have been involved in this line of work, and what I presented today, I want to thank all of them for the work that they've done, and I want to thank you for being here today and listening to my talk. I will take questions.
Fantastic. Thank you, Nika. Any questions? There's one back there. You want to stand up, please? You mind standing up to ask your question?
Oh, okay. People can hear me. Oh, okay. Did you say to stand up? Okay. Great talk, and for someone who wasn't in this field, I was able to grasp a lot of it, so that tells great teaching abilities. So coming as a practitioner in the healthcare field, and what you mentioned, oftentimes we go with training based on certain incidence distributions in the population we see, but when we go and deploy, those distributions are not being maintained. So from a practical consideration, how do you propose we handle that, particularly in the regulatory frameworks where you're not allowed to change the model once you are frozen in that space? That would be one. And then a related question is, if you're using a fine-tuning approach, how does the catastrophic forgetting aspects of it come into play in such multi-objective learning?
Great questions. So let me say that a few things about the regulatory approach that you asked. So one reason that we specifically want something that's not personalized, this like function f rather than fi, is actually to address what the need of this field is, which is that you don't want to change the model, both in terms of time and in terms of what population or where it's being deployed. In fact, legally, a lot of times you cannot. So in some sense, actually, this perspective is very much about providing those guarantees. But at the practice level, what it's saying is that you do need to have an imagination about the ways that your data can shift. You don't need to observe them, but you need to at least be able to kind of imagine what they look like. in other words, what multi-objective guarantees can provide is to say that the model that you learned, if you kind of imagine the ways that your data can shift, is going to be valid for a long time until the shift becomes strong enough that it no longer is. So it actually comes with a guarantee that, like, it could come with a guarantee that says that it's valid longer than if you just trained without multi-objective, but it's not going to be valid until the end of time. Some adversarial shift that if you never imagined it is going to still cause a problem. The second question was about fine-tuning and catastrophic forgetting. Let me first say that we are not fine-tuning. I was just saying that for fine-tuning, this has some implications. But if I were to take the implications to the maximum, and this is a result I didn't demonstrate here, it's actually ongoing work, what we show is that, just how I said you have to be adaptive, you actually have to be adaptive quite a while. So you cannot just fine-tune once. You, in fact, keep having to go back and forth. And both our results, and there's some other results, again, none of these are about fine-tuning, but the implication for fine-tuning means that you cannot hope to just fine-tune once, or like train and fine-tune once, but you in fact need to allow yourself to go back and forth about logarithmic number of times. So this is the insight that I would say, that if you're hoping to overcome catastrophic forgetting, either you need to actually have a more involved fine-tuning pipeline, or you need to think about the scale in a different way. Like your fine-tuning task might actually have to have data that was at a larger scale and that was part of your pre-training. Okay, other questions?
Time for one more question.
Thank you for your talk.
My question is, do you see any parallel with your work with active learning?
Parallels with active learning?
Yeah.
A lot and not enough. So active learning is the field that says that I want to actively ask for labels rather than actively ask for samples. So the paradigms are similar in the sense that you're still very much are about interactive ways of deciding where you need information, but the form of that information is quite different, and I think it's consequential. Here, it's not just about labels. You can actually add active learning as another layer on this. But here you're actually deciding where to take your covariates, which is very different than at least how active learning is thought about. If I were to think more broadly about interactive learning, I would say that absolutely both of these are saying that there is a lot of value and there's a lot of saving that can come from deciding what granularity of information you need at what point.
Thank you.
All right, let's all thank Nika again. Thank you very much.